All right, so we're going to look at the electric potential of a sphere. First, we're going to do outside, then we're going to come back and do inside. And then we're probably going to do two cases, one where the sphere is hollow and one where the sphere is solid. And then from there, if you want to, you can take it further and do, non-uniform charge density or uniform charge density. But let's first start with the outside case. So it doesn't matter what's going on the inside for the outside case, because we know that the electric field, by Gauss's law, should be 1 over 4 pi epsilon naught times q over r squared, right? And this is for r greater than r. Okay. So now all we have to do is say my potential is minus the integral from, we're going to do absolute potential. I don't care about potential difference. I want absolute potential in this case. So infinity to, because we're bringing in from infinity, we know the potential at infinity is 0 to some variable distance r. So this will get us the value for any distance we want to be away from it. So then it's going to be the electric field, 1 over 4 pi epsilon naught q over r squared dr, because r is our integration variable here. We want to move radially in. I mean, once again, it doesn't matter if you want to curve your way in, as long as your motion is inward. That doesn't matter. We can circle around or spiral in. Doesn't matter. All we care about is the difference for how far you've moved radially inward. Now, when solving integrals like this, I know that you guys are all calculus experts at this point, but I personally like to rewrite them. So it makes it harder for me to miss minus signs and harder for me to mess up the exponent. So let's write that constant again, which we'll pull out next time. Let's put the q with it. Might as well, because we're not integrating the q. And it's going to be r to the negative 2 dr. So now it's easier for me to look at that and say, okay, I need to go up 1, and up 1 isn't 3, it's negative 1. It also helps me keep track if I pull that minus sign down. So this is going to equal minus q over 4 pi epsilon naught, it's 4, times r to the negative 1, or 1 over r, and can't forget that minus sign, right? Evaluate from infinity to r, and so this is just going to be, because 1 over infinity is 0, so this is just going to be q over 4 pi epsilon naught r is equal to v. Okay, so that's how you do it outside. Now, let's go ahead. So let's do the case where it's hollow first. That's going to be easier. So when it's hollow, my electric field is 0 because the charge enclosed is 0, right? If I want to make my Gaussian surface inside, I know that the charge enclosed is 0, so there can't be any electric field. And since I also know that E equals minus dv dx, or once again, if you want to be real pro, minus grad v, the gradient of v. Yeah, so that since we know that the electric field is 0, we know that my potential is not changing. So whatever inside, the potential is a constant. Whatever that constant is, we'll have to figure that out in a second. So this tells us that potential is constant for r is less than or equal to r. All right, so let's actually do it. So now you might be tempted to integrate from infinity to r again, like we did here, coming inward. And you do want to do that, but you have to realize that your electric field is actually piecewise if you do that. You don't have just a single electric field. You have, your electric field would be defined as 1 over 4 pi epsilon naught, 4, q over r squared for r is greater than r, and then 0 for r is less than or equal to r. So you have to do your integral in 2 steps. So your integral actually will need to look like v equals minus infinity to capital R of 1 over 4 pi epsilon naught times, I keep wanting to do little q, but I'm using big Q right now. Big Q over r dr squared, dr. And then you want to add the integral from r to little r. Because as we move inside the circle, we're now, we'd be saying little r is somewhere in here. So this is going to be, well, 0 dr, right? Yeah, so this term isn't actually going to matter, right? Because when I integrate this, it's just going to be some constant. And that constant is then going to do, it says a definite integral. It's going to subtract itself out. So this term is gone. We don't care. So now the first term is all that matters. And I already know how to solve the integral. We already know that v is equal to q over 4 pi epsilon naught r, because I'm now plugging in this r into here. So that is going to be my answer for inside of a hollow sphere. So if I want to quickly graph both of those, or my potential as a function of radius, it's going to look like out here it's going to go like 1 over r, and inside that's going to be r. Let's make sure I label my axes, r, and this is going to go like 1 over r, and up here is constant. And if I'll be real particular, just in case AP is real particular, I'm going to make sure I call this guy volts and say the units for this guy are meters. Oh, you can't see my bottom of my graph there. All right, but that's what that should look like. And now let's go ahead and talk about a solid, uniformly charged sphere. Now, if we have a solid, uniformly charged sphere, the outside potential is going to be the same because it's all about the charge enclosed. So if I draw my Gaussian surface around the outside of it, the charge enclosed is still Q. But if I draw my Gaussian surface in here, the charge inside is not Q, right? The charge inside is less, and it depends on the volume. So to find the total charge using the fancy calculusy way, which is good to know because you might get some that are non-uniform charge density, and I'll talk about that at the end if I remember, because sometimes I forget. Yeah, so to find the charge, I know that the total charge is equal to the integral of the charge density dv, right? So if you know how to integrate dv, you can do a triple integral and do all that. Or we can kind of cheat and say, well, what if I say let's have a spherical shell? So, just a hollow like sphere, a hollow ball, and we just keep lining them up and stacking them up. So I'm actually going to say, the Calc 3 way would be, say, dv is equal to r squared sine theta dr d theta d phi. If you guys aren't comfortable doing that or think this other method will be faster, you are completely fine to do this. So the way that AP wants you to do this, because technically you don't need to know Calc 3 for this class, though sometimes it's a little bit helpful. The way AP wants you to do this is they want you to say, well, why don't I just say that I have the surface area of that sphere, and I keep stacking those up, and those are infinitely thin, so you've got some surface area of with this, given area, right? With area ds or whatever, I don't care. But it's going to be, so you're going to take your surface area equation, 4 pi r squared, and you're going to integrate that outwards as you stack those on top of each other. So AP wants you to start here. But this is by far the more fundamental version. But this is, since we only require Calc 1 technically for this class, this is fine. All right. So let's go ahead and put that in, because we're not looking for the total charge. We're looking for a smaller bit. So I'm going to call it little q. And we're going to integrate from 0 to r of rho times 4 pi r squared dr. So in this case, the charge I'm enclosing, so this 4 pi and this rho can come out, and I can just integrate. I can take out 4 pi rho from 0 to r of r squared dr. I think all of you guys can solve the integral pretty easily on your own. So we are going to get q is equal to 4/3 pi r cubed times rho. Or you can put that rho earlier if you want. So really this is the volume of the sphere I'm making inside times the charge density, which makes sense. So because we really defined charge density, another way we could have done this, we're smart, would be q over v, right? Which is pretty much what we got. This is volume q. We're good. So how do we use this now for potential, right? How does this affect our potential? Well, at the surface, it's still unchanged because our electric field outside is unchanged. But now inside, I have less charge. So I need to figure out my electric field. All right. And we do that by saying the electric field is equal to the charge enclosed over epsilon naught times my surface area, right? Or charge enclosed over 4 pi epsilon naught times r squared. Now, perhaps a better way of doing this would be to put the actual integral in here. So to do, I guess you could, it's still charge enclosed. So I guess it's the same thing. So 4/3 pi r cubed, or 4 pi r squared dr times rho up here. But you don't have to do that. You can do it the way we've done it. So let's go ahead and take this line, this section down, and just plug in for our charge enclosed. So I'm going to now say that 4 pi epsilon naught, let's pull that out front. And I've got 4 over 3 pi r cubed, and this is over r. So I can do some canceling. I can take this r squared down here, this r cubed, and cancel with this term here. So I've lost that. Take that 4 and cancel with this. So my electric field inside is going to be, oh, I forgot my rho up here somewhere, right? Rho. Awesome. So my electric field is going to be, let's simplify this. Oh, my pi's cancel too. Look at that. So nice. So wonderful. 1/3 rho r. Not bad. So to get my potential, I need to integrate that, right? So we know that V equals minus integral from infinity to R of same electric field as the outside, right? Because we're breaking this apart like we did earlier, times Q over R squared dr. And we know what the answer to that integral is. We've already done that one. We'll just write that down in a minute. I'm just showing you the full thing again, plus negative integral of rho r over 3 dr. And this is going to be from r to little r. Or we can call this guy, have different variable names if you're uncomfortable having the same variable here as here. But it really doesn't matter because it's all notation. All right, so let's go ahead and do this. We know this first integral, we know the result is going to be 1 over 4 pi epsilon naught q over capital R. And we know that the integral over here, we're just squaring that, right? And bringing down a factor of 2 is going to be rho over 3 times, I guess bring down a factor of 2, so let's make this guy a 6. And this is going to be r squared, evaluated from r to r. So let's go ahead and finish that one, I guess. Epsilon naught q over r. And then when we evaluate this, we'll do, I forgot my minus sign here, didn't I? All right. So we're going to just flip our bounds when we, with the minus sign. So I'm going to do plus rho over 6 times r squared minus r squared. Okay, so this looks gross. And one of the issues that we have here that I don't like is that the problem didn't give us rho as a starting point. It gave us q. So I want to put rho in terms of q, just because I like to give my answers in the same form the problem gives, with the same, variables and constants the problem gives. So what I know from earlier is this relation here. I can replace this with the whole volume. If we're talking about the whole charge, I can write it like that. So let's go ahead and replace rho with that, q over 4/3 pi r cubed, or I can put the 3 up top if you'd rather. So 1 over 4 pi epsilon naught q over r, because that term hasn't changed this whole time, plus 3 q over 4 pi, because the v's going on the bottom. Where'd my term go? Sorry, I just lost where I was looking for my notes. R cubed. For some reason I couldn't remember the volume of a sphere. And it's going to be times r squared minus r squared. So if I want to simplify this, I can still have that. Let's factor out the, I lost my epsilon naught somewhere, didn't I? Somewhere I'm supposed to have an epsilon naught down here. Yeah, that's where it was, right up here. But if you guys know you're supposed to have an epsilon naught and your time's short, because you only have 45 minutes for this exam, just write it down here and then maybe track it up. It's not really important. So let's just track this guy back down to make sure we've got it. Epsilon naught, epsilon naught, epsilon naught, epsilon naught. Okay. So now I'm going to have 1 over 4 pi epsilon naught, and let's factor out a q also. And let's even factor out that extra r on the bottom here. So I'm going to factor out this whole term. So times 1 plus 3 over r squared times r squared minus 3 over r squared times r squared. So obviously those guys cancel. And we have our answer in one line once we simplify. So simplifying this down, we get your potential is Q over 4 pi epsilon naught R, the same format you like, times 1, I'm sorry, not 1, we're going to have 4, I guess. 4 minus 3 over 3 r squared over capital R squared. And that's going to be that. So I was about to move on to the next part, and I realized I made a mistake. And I like to leave my mistakes in these videos so you guys know that a couple things. One, how to find your mistakes and realize you've made one. And two, to realize that even a doctor of nuclear physics sometimes screws up because, it's hard to keep track of things when you're doing stuff on the fly and it's messy. And yeah, so what I realized is that this 6 never actually went anywhere, right? It just kind of disappeared. So I really should have a 6 down here, which means that this and this cancel. So I now am going to turn this guy into an 8 from that. So now with that 3 gone over here, and that's going to, these are both gone, right? Yeah. So I'm going to, this first term here is going to be, going to go into, well, hold on, let me track this. So we got an 8 down here, so I need to have a 2 on each of these once I pull that out. Yeah. Check that out. So now down here, if I put this in the format of, well, I guess let's just go ahead and rewrite this line up above so it's easier to keep track of. I want to write this as Q over 8 pi epsilon naught R times 2 plus 1 minus R squared over R squared, capital R squared. So that's the line I want. So down here, let's just cross this off. Should look like V equals Q over 8 pi epsilon naught times R, and this is going to be 3 minus R squared over R squared, capital R squared. So in the limit that we set our little r equal, so this is how I realized I was wrong, by the way. In the limit that we set our little r equal to big R, what we should be able to have the same value that we did in the hollow sphere, because at that surface it doesn't matter. So when we're at that surface, those two values should agree. So if I set it here, little r equals big R, then this term's 1, this whole term becomes 2, and I then get Q over 4 pi epsilon naught times R once I cancel. Yeah, so just that little mistake kind of cost us and made it worse. So now if we wanted to do a non-uniformly charged sphere, how would we do this? So I'm not going to spend a lot of time because this is a long video already. I think this is the longest one I've ever done. You're welcome. All we would do is when we're doing this integral here, or this one here, that rho term will have an r dependence, right? So let's just make a little side note. Make a little side box. There we go. I would say when we're finding our q, we're going to get q equals integral of rho dv still, right? But we're going to say rho, let's say rho has an r dependence. So rho equals some constant times r, let's say. Well, so now when I solve this integral, I'm going to say this is actually going to be kr dv. I'm going to plug in for dv. I'm going to get kr times 4 pi r squared dr. So this is going to be 4 pi k r cubed dr, and we'll have my q term will end up being 1/2 pi k r to the fourth. And so then you'll just take that value to where we used q earlier, and you're going to plug that in instead. All right, I hope this helped you guys, and I'll see you in the next video.